Hello everyone. We are starting this Galois theory discussion for first week. There are first we will recall things. Okay, what has been done in the class in the first week, and then we will see uh, some exercises which are not blue colored. I will discuss them with you. Okay, so first only few things which I'm mentioning here are. That historical perspective of Galois theory, and then examples of fields in the second lecture. Third lecture was about polynomials and their basic properties that we have learned from high school, and then polynomial rings, and then unit and unit groups. These are 5 lectures in the first week. Okay, so we'll see some of them. Uh, let's say we discuss some for what is commutative ring. If everyone is familiar with that, I can leave that. Otherwise, I can write few properties of this. So let's say I'm writing commutative ring or commutative rings. Is it visible now? Someone reply, is it visible? Okay. So these are the properties if you recall from classroom, that if R is abelian group and R plus is abelian group, R dot is semi group. Semi group it just means closure property, and okay, let me write it here. Closure property and associative associativity. These two properties uh, in R dot. So these are called distributive property. Distributive. Then we say R plus together with this dot. This is commutative ring if it satisfies extra property that A dot B is equal to B dot A. Okay. Here are some examples: Z, Q, R, C, complex numbers, and polynomial rings, which is material of the second lecture. So what are polynomial rings? For example, ZX. ZX is just uh, collection of these formal expressions a1, a0, a1x plus a(n)x power n, where this all ai belongs to Z, and all the n belonging to natural numbers union 0. Okay, so these are called polynomials. There are rules to add two polynomials, multiply two polynomials that you have seen in the classroom, so that I'm not recalling that part. So this if you have, let's say, px a polynomial and qx a second polynomial, you want to add them, you just add them with degree wise, right? So if first one is, let's say, a0 plus and so on a(n) x power n, and second is b0 plus some bm x power m, then their addition will be just a0 plus b0 plus a1 plus b1 multiplied with x, and so on. where if m is less than n, then somewhere bm plus am x power m, and then am plus 1 x power m plus 1, and so on. This is that rule, plus an x power n, something like this. Okay, so multiplication is different. Multiplication of px into qx is this, a naught into b naught, and the second one is a naught b1 plus b1, sorry, b0 a1 into x, and so on. This kind of expressions will come, where uh, you can write it like c0 plus c1 x plus and so on, plus c k x power k, where each ci is this summation, uh, let's say p, sorry, p and q, m into m plus n, m and mn also appearing here, so we can choose something else. Let's say cd, c plus c is up, fg, okay, f into f plus g is equal to I, and these sums cf into, sorry, af into bg's, so that their sum will be equal to f plus g is equal to I. This is your uh, ith coordinate. Like for example, this is c1 and this is the sum for that. So this kind of multiplication is defined in polynomial rings, and then zx becomes ring. Okay, with these two this multiplication and this kind of plus, it is defined degree wise or coordinate wise. This is ring, commutative ring, in fact. Okay, check it, because z is commutative. It happens so that zx is commutative ring. Okay, so let's see what is unit and unit groups in a ring. Okay, so r plus dot, let's say it is a commutative ring with unity. Okay, commutative ring with unity. With unity means just that there exists one inside r, such that 1 multiplied with any element of r is r, either from the left or from the right. Okay, or every r. Okay, so let r be a commutative ring with unity, then r star, this is set of units or collection of units in r. Units in r means those elements of r which are invertible in r. Okay, for example, look at this invertible. Let me explain for that. A belonging to r is said to be invertible, is invertible, or is unit if there exists b in r such that a into b is equal to 1. Okay, this one, which is unity of or identity of r. Okay, so actually there is some problem in device. Let me see if it is recording or not. I hope it is recording so that I can upload this video after some time. So this is all in a ring. R star is just a belonging to r such that there exists b in r depending on A, of course, such that A into B is equal to 1. Okay, B into A will be anyway equal to 1. Why? Because we are taking commutative ring. Okay, so A into B is equal to B into A. So this is set of units, and this forms a group. R star is a multiplicative group with this operation. Multiplication of R only. R star with dot is a commutative group or abelian group, because R is any, we have taken R commutative, so this is an abelian group. So after this, let's see our questions which are given in the exercise. So first question was that let R be commutative ring. Whenever I'm recording on my device, it is stopping somehow. Sorry for that interruption. Let R be a commutative ring, and let A prime, B prime belongs to R. Okay, these are elements of R, so that there exists unique ring homomorphism. So that there is a unique ring homomorphism. Ring homomorphism, I hope you know the definition. I will recall it. Ring homomorphism FAB from Rx, which is polynomial ring over R, to Rx, such that FAB of C is equal to C for every C inside R. I mean, for constant elements of R is said to be constant polynomial. So for constant polynomials, FAB is acting like identity map. Okay. For others, for X, FAB of X, this is coming out AX plus B. Okay. So we have to show that there is a unique ring homomorphism of this kind, FAB. Then there are more questions related to this. We will come to them with time. Okay. So first, let's see how to define such a ring homomorphism. So what are ring homomorphism? Ring homomorphism. Let R be a ring, R and S be a ring. Let R plus dot and S plus dot. They're different. Okay, let me write like this. These operations are different in R and S. Okay, so there are some different kind of multiplication and different kind of addition in other ring. At RB, R and S be two rings. Then phi MA from R to S is said to be ring homomorphism if, first of all, it is sending 1 to 1, 1 of R to 1 of S, and second is phi of A plus B is equal to phi of A plus phi of B. Okay. Third is phi of A into B. This goes to phi of A into phi of B for every AB belonging to R. Okay, this is definition for ring homomorphism. Now we are coming to our question. R be a commutative ring, and we are talking about homomorphism in polynomial ring. Okay, such that it acts on constant as identity and on X like this. So let's see if we have how to do this. In Rx, elements are like A naught plus A1x plus A2x square plus and so on, an x power n, right? This kind of elements are in Rx. So if we want to define a ring homomorphism from Rx to Rx, how to define? We'll use ring homomorphism properties like these 1, 2, 3 properties and see how it comes. Okay. And we also want ring homomorphism with these conditions that on constant it is acting as identity on, and on X it is giving Ax plus B. So phi of A naught plus A1x plus and so on an x power n. We want to apply phi on this because phi is a ring homomorphism. We use property 2 to write it like phi of A naught because A naught is also a polynomial. These are all elements of Rx and their sum is also in Rx. So this element was initially in Rx and these are also in Rx. Okay, they're also polynomials. So we can write phi of A1x and so on, phi of an x power n. Now, if you see here x power n is appearing. If there is x square, it can be written as x into x, right? So once you apply phi on x square, I mean phi of x into x, what it becomes? Using third property, it is multiple of phi x with phi x. Note that operation in Rx, both sides, they are same. So this dot is same as this dot. So they are equal. This is just the same dot. So this becomes phi of x square. Similarly, if there is x cube can be written as x square into x, and then that will become phi of x cube will become just phi of x whole cube, right? Use these properties. Okay, then you will get this phi of a naught plus phi of a1 into phi of x plus and so on phi of an into phi of x power n, that will become phi of x whole power n by induction using this uh, rough calculus. Okay, so use that properties here. This is second property implies this equality. Third will imply this. Now we want our homomorphism such that it is acting as a constant on it is acting as identity on constant polynomials, and on x it gives ax plus b. So we just replace them. uh, in this place we want just a naught only, in this we want a1 only, but phi of x we want ax plus b. Okay, so everywhere you do the same. So an, this is coming out ax plus b to the whole power n. Now what is this written? This is just f of ax plus b, right? In place of x in the initial polynomial, we have just replaced x by ax plus b, right? So we see this polynomial should work. Uh, okay, this homomorphism should work for our ring homomorphism. So we define FAB of some px is equal to p. In place of x, we are just replacing ax plus b. Now verify that it satisfies it satisfies given conditions, right? How? Someone can point it out how it satisfies our given conditions. FAB of c will be the constant polynomial c evaluated if, because there are no x, we don't want to replace x by ax plus b, so it is again c only, so nothing to check. And on x, f of a b evaluated at x, what it will be? It will be in place of x we want to replace ax plus b, so this is just ax plus b. Okay, so this polynomial, this ring homomorphism satisfies. Okay, we want to check if it is ring homomorphism or not. F A B from Rx to Rx defined by okay. So wherever you see x like this, I'm writing somewhere x like this and somewhere like this, so they are same. Okay, so don't be confused if it is capital or small letter, so they are same in my handwriting, sorry. Okay, so defined as this is ring homomorphism. So first of all we want to check FAB of 1, it is going to 1, right? Because it is constant polynomial. We checked here. So in the second, f of AB, P plus Q, two polynomials. So it will become, let's say P is summation AI x power I. Some this is finite sum, okay? Ending somewhere, let's say degree n polynomial, I from 0 to 1. And Q is, let's say, some polynomial uh, BI x power I. Sorry, BJ x power J. J running from 0 to some M. Okay. So this will turn out to be f of AB and this sum becomes ai plus bi x power I. So I'm not writing index because in the sum, this index will be going to k, where k is maximum of m and n. Usual sum of polynomials. So if they are equal, then nothing to worry about. If they are not equal, we'll make them equal by adding extra. Let's say if m is less than n, then we'll take b m plus 1 is equal to 0 up to bn is equal to 0 and make our polynomial till degree n. Okay, to make to add them. Okay, so but in this case, if you replace ai plus bi x by ax plus b, here ax plus b, here we have this that same sum I from 0 to k. You can usual polynomial property of polynomial, you can split it again, so it will become ai ax plus b. Sorry, it here it was, we are replacing x by ax plus b, so power of x remains I. Okay, uh, plus summation bi ax plus b power I. I'm not writing index, so you can write it explicitly if you wish. So, so the first one is nothing but p of ax plus b, and the second one is q of ax plus b. Okay, so you can check third one also. Okay, this is exercise. So FAB is ring homomorphism. Okay, so we find some ring homomorphism. Now we want to check if it is unique. Okay, because there it was said unique ring homomorphism. If there is let's say some other phi rx to rx be some other ring homomorphism such that phi of r is equal to r for every r belonging to ring r, and phi of x is equal to ax plus b, then phi of a, we want to show that we want to show that phi of phi is equal to fab, right? Then this fab is unique in that sense, right? Okay, so how to show these two maps are equal? FAB is also mapped from Rx to Rx. Phi is also mapped from Rx to Rx. To check two maps are equal, we can check element wise they are equal, right? We want to if we can show P of Px, Px is any polynomial is equal to FAB of x, AB of Px for every Px belonging to Rx polynomial ring. This is all we want to check. Then P and FAB are equal. So FAB is just a unique map with these properties. So how to show this? P of some Px, we are evaluating at it, and Px be same thing. Initially it was summation ai x power I. Px be a naught an x power n. Then this becomes phi of a naught plus phi of a1 into phi of x plus and so on phi of an phi of x power whole power n it becomes. Okay. But you see here, if you use this property phi of r is equal to r for every r inside r, this constant becomes same constant a naught, and this becomes a1, but phi of x becomes ax plus b, right? Ax plus b and so on. This becomes an, and this is just ax plus b power n, and this is nothing but p of ax plus b, and p of ax plus b is nothing but, as we define, fab of x, fab of px, sorry, right? So we wanted to show this, and we shown this. P of px is equal to fab of px for every px in Rx. We I should not write here for every. What is wrong in here? Can you point it out? What is wrong? Why I should not write here for every px belong to Rx? Okay, let me say here, because I fixed px and then I evaluated at I found it is equal to fab of px, right? But this is for particular px. I should write here similar proof, similar thing holds for general px. So this is for particular thing. So I think I should not write it here. So this is somehow not making sense. So, but this is true if px is anything. Okay, this is true because we chosen these coefficients are random in R. So this holds for all px in Rx. Hence, phi is equal to fab. Okay, so uh, this is unique ring homomorphism, and what extra we wanted to prove in that question was determine composition of these maps. F A B composed with F A prime B prime. Okay, composite map. Okay, so first map was Rx to Rx, which is of this one. This is first map F A prime B prime. Second map is also from Rx to Rx. So this composite map is from Rx to Rx only. Okay. And how to calculate this? Let's say we take a polynomial px. As usual, px is just a0 an x power n, where this n is maximum such that an is non-zero. Okay. Then let me write here. An is called leading coefficient. Leading coefficient of px. Okay. So what I'm telling here f a b composite with f a prime b prime evaluated at px. So first it will f a prime b prime will apply on px and then f a b. F a prime b prime on px. So what it is coming? This one becomes p a prime x plus b prime, right? X is replaced by uh, a prime x plus b prime, right? So now we want to apply fab on this polynomial. This is some new polynomial, right? Where uh, on px we have replaced x by a prime x plus b prime. This is something, let's say, gx. Now here we want to replace x by ax plus b, right? Ax plus b in this step. So what next polynomial will become? Let me try writing it out. This will become p a prime. X is replaced by ax plus b prime as it is. So this is our if this is equal to gx inside polynomial, then this polynomial is okay. If gx is equal to p a prime x plus b prime, then g ax plus b, this is nothing but p of a prime ax plus b prime. Okay, so check it, then you will find this. Okay, so the composition is nothing but p. This is a prime a x plus a prime b plus b prime. So what we are getting here, this is also again of the same form where x is replaced by some cx plus d, right? Where this is the first constant, this is the second. So this is nothing but f a prime a comma a prime b plus b prime of px, right? If you have doubt, you can ask me. No, I am audible, right? Okay, so I hope you don't have any doubt here. So if you have any doubt, you can ask me. Okay, otherwise I will be speaking, and I hope that you all understand. But at the end, uh, you have many doubts, and you have not asked anything. So this, I hope you understand the composition. So this is for random px. So f a b composed with f a prime b prime. This is nothing but f a prime a comma a prime b plus b prime. This is our composition. So the next thing in the question, it said that further so that if a is a unit, a is a unit in R, then FAB is an isomorphism. Is an isomorphism. And find its inverse. Okay, so let's see what to do to get inverse. So first, let's see what is identity morphism from Rx to Rx. Rx to Rx. Identity map. This is also ring homomorphism, right? Identity map is just string homomorphism. If let me write it as ID, or let me write it as just small I. Okay, then small I of a plus b is again a plus b. Small I of 1 will be 1. Small I of a into b is just a into b, because this is identity, and all of these are ring homomorphism properties for I. Okay, so ID is ring homomorphism. Can we write I as FAB? Question mark is I is equal to FAB or some AB? Someone can speak me, help me out finding A and B here. So FAB was like FAB when applied to PX. It becomes P of AX plus B. And what we want, that FAB equal to I. That is, we want this is equal to I of PX, right? But I of PX is just PX because I is identity. So if we take, it is clear that what should be A. If A is equal to 1, B is equal to 0, right? Then FAB is nothing but I. Understood this part? If you understood, you can say yes. Okay, so we have an identity homomorphism, ring homomorphism from Rx to Rx, which is of this form F0, sorry, F10. Okay, this is F10. F10 is identity, which is an isomorphism. This is an isomorphism, is because this is just identity, is an isomorphism. Okay. Now let's see. Let FAB is given, and we want to find its inverse. And what extra is given? Let assume. Okay. Let me go. Assume A inverse exists. Okay. That is, A inverse exists means A is invertible or A is unit. A is unit given. Okay, so we have A inverse, and now we want to calculate inverse of FAB. FAB is some ring homomorphism. Let its inverse be like FAB inverse be same kind. F in some A prime B prime. We don't know if it is of this form, but we'll see if it is or not. Okay. some A prime B prime. If we find such A prime B prime, it is enough that this will be our inverse. So we will use inverse properties of FAB and we'll get A prime and B prime such that this all holds together. Okay, so we have already calculated this FAB composed with FA prime B prime. This is nothing but F sorry FA prime A plus A prime B plus B. FA prime A comma A prime B plus B prime. Okay, so if we want something to show inverse, so let's say this is inverse of the first. If we compose them, and we'll get identity. Okay, so that is enough to show that uh, they are inverse of each other. Okay, A inverse is B if and only if AB is equal to identity in any group. Okay, so but here in this case, because they are all homomorphisms, we want identity homomorphism as the product. So we want this to be I or just f of 1 comma 0. Okay, so what to take? What to take A prime B prime? Guess what we want? A prime A is equal to 1, A prime B plus B prime is equal to 0, right? So take A prime is equal to A inverse, then you see it becomes 1. Okay, so what about B prime? B prime you take minus of A inverse B from here in the second. Understood. So now you have two more maps, let's say F into G is equal to identity, right? This shows F inverse, or we need to okay. Okay, let me see. Wait a minute. We should show F inverse is just G. Okay. What about this is coming out right inverse because morphisms basically homomorphisms, group of homomorphisms, they are not abelian groups. So F into G is equal to identity. But what about G into F? Okay, sorry, F composite G is identity. What about G composite F? That also we have to check. So let's see F A prime B prime composed with F A B. What it will be? F A prime A comma A B prime plus B, right? This position of A primes, they are changed. Clear? This is just A prime because R is commutative ring. So what happens to this? A prime is again 1 as A inverse. A prime is A inverse. So it is 1. What about this? Let's calculate here. A into what is B prime? B prime is just minus of A inverse B, right? Plus B. But what is this coming out? A into A inverse becomes 1 minus B and then plus B, it is 0. So it is 0. So from here we get the composite F is also identity. So we conclude this. F inverse is G. Okay, left and right both inverse. Now in the first hand, if you see where it is, we got F composite G, where F stands for FAB and G stands for FA prime B prime. Or from here, it is also clear. It is okay. F inverse exists and it is like G. What to write here? I'm sorry. It is clear that F is an isomorphism or say invertible, and its inverse is inverse FAB is F A inverse minus A inverse B, right? Okay. So we got FAB inverse is equal to FA inverse minus A inverse B. So first question is complete. Okay. If you have doubt, you can ask me at any step. I will go back. Do you have any doubt or I can continue? Continue. Okay. So let's see about the second question, what it says. Let A be a field and A, B belonging to K with A not equal to 0. We have to show that degree of FAB of Fx is same as degree of Fx for every Fx belonging to Kx. And the second we will write again. Okay. It says that every irreducible polynomial through FAB. FAB is the morphism in the first question. Irreducible polynomial goes to irreducible polynomial. Okay, that is the second. Let me write here. B is the if Fx belonging to Kx is irreducible, then FAB of Fx is also irreducible. Okay. This is your question. How to solve this? So, what is degree of Fx? Degree Fx. What is degree? If Fx is the polynomial, let's say A0, I'm writing again same thing, A0, A1x, and so on, an x power n. So largest n such that an is non-zero. This is nothing but largest or biggest, whatever. Biggest n such that an is non-zero, then n is called degree of fx. Okay, so let's see what happens in degree of we are taking f to be degree of degree equal to n. Let degree fx is equal to n, and we want to show that degree of this is same as degree of fab of fx. Okay, this we want to show if it is equal or not. This part we are taking. Let me write. This is our question. How to do this? We'll calculate what is inside polynomial. Okay, and we'll see some good thing. Let's see fab of fx. So this is nothing but a0 plus a1 ax plus b, right? By definition of fab, and so on. An ax plus b power n. So if we want to get, okay, here n is called degree and an is called leading coefficient. I'm mentioning this second time, but it is important. So what happens to leading term, that matters to calculate degree, because this doesn't appear in the definition of degree. Okay, we want largest possible n such that the coefficient is an is non-zero. So here, if you see, if you expand this last term, what will happen? Some lower degree term plus here it is an into a power n into x power n, binomial expansion of the last term I'm telling you, plus lower degree term, lower degree terms okay. So largest degree term is uh, since an is sorry since a is non-zero in k and k is field, hence a is invertible, a is unit. So because k is field, every non-zero element has its inverse. Okay, what is the property of fields? Let me write here. K is a ring with these properties. K with plus is abelian group. K after removing 0 with dot is an abelian group, and distributive property holds. Okay, a plus b into c equal to ac plus bc. So these are the properties of fields. So if a is non-zero element in k, then it comes into this and it is invertible. Every element in abelian group has its inverse. So from that a is unit. So any power of a will be unit. So an into a power n into x power n plus lower degree term. Lower degree. This is fab of fx. Because a is unit, a power n is not zero. An is anyway not zero because f is of degree n and an is non-zero. We are assuming here we are always we are assuming an is non-zero. Okay, wherever it is appearing. While we are taking this says an is non-zero in fx. So an is not zero, a power n is not zero. So their multiplication is not zero. An into a power n is not zero. This implies degree FAB of fx is n. Okay, and which is degree of fx. In the classroom, if you carefully listen this, fields are integral domain. A is field. It implies integral domain, but not converse. Okay. Integral domains means whenever AB is zero, this is extra discussion out of. Whenever AB is zero, either A is zero or B is zero. This is integral domain. So because here an is not zero, a power n is not zero, so the product is not zero. That is why larger degree term is again n only. So we calculated first part of the question. This part is done. Degree of FAB of fx is same as degree of fx. Now we want to calculate that if f is irreducible, it goes to irreducible polynomial. Okay, how to see this? Part B. F belonging to Rx, or no, here in particular we are taking Kx, right? K is field. Kx be irreducible. We want to show FAB of F is irreducible. Now notice that Kx is integral domain. Right? Note Kx is PID, principal ideal domain. It is domain that is integral domain. How to prove this? Because since K is integral domain. It was discussed in the class. Okay. Oh, what happens if FAB of F is reducible? We will look into that case and see. Oh, note that A is non-zero given. Since A is non-zero, it implies A is unit. A is unit using now use first exercise. What we get FAB is isomorphism. Isomorphism. Okay. FAB is an isomorphism. Now, if FAB is irreducible, FAB of F, it can be written as let's say P into Q, Px into Qx. Wherever I'm writing polynomials, let's say F, it is assume that independent variable is x hidden there. Okay, fx, FAB of F, it is written as Px into Qx, where uh, P, degree of P is bigger than or equal to 1, degree of Qx is also bigger than or equal to 1. Then what happens? This Px Qx is also some FAB of Rx into FAB of Sx. Why? Now I'm asking at this step. Someone reply. Why this Px is equal to some Rx and Sx? Are you able to speak? You can unmute yourself. If permission is not given to you, I can allow you to unmute. Yeah, you can unmute now. Okay, I'm giving you this hint. FAB is an isomorphism. So in particular, it is surjective. So for any p, you will get this. Okay, some Rx, Px can be written as FAB of Rx, since FAB is an isomorphism. Now you just look at it. What happens? FAB, this is written Rx into Sx, right? And here this side you have FAB Fx. Now use that F is 1 1. You will get Fx into Sx, since FAB is an isomorphism, or in particular 1 1. Note that from 2a, what we have, degree of Rx is equal to degree of FAB of Rx, right? And what it is? Degree of Px. FAB of Rx is just Px. And degree of Px is just bigger than or equal to 1. If it is degree 0, I'm saying they are units. So I'm assuming in this case that if F is reducible, FAB of F, sorry, if FAB is reducible, then FAB of F can be written as this, and degree of P and degree of Q, these are bigger than or equal to 1. If one of them is 0, this factorization doesn't make sense, because degree 0 elements will be constants, and that constants are units. So we say an element is irreducible if any factorization like P into Q, one of them should be unit. So we want something which is reducible. So for that case, we want degree not equal to 0, degree bigger than or equal to 1, so that it makes sense that this element is reducible. Okay, so what we get? Rx and Sx, both are degree bigger than or equal to 1 by the same logic. Similarly, degree of Sx is bigger than or equal to 1. This implies Fx is reducible. And this is contradiction, because Fx was irreducible, right? Fx, we took an irreducible element, and we wanted to show that its image is also irreducible. Okay, for that, what we use that Kx is integral domain. So any and also any non-zero element is unit. Now exercise 1 shows that FAB is an isomorphism because A is not 0. Now if FAB of F is reducible, this means it can be factorized at Px into Qx, where Px and Qx are both degree bigger than or equal to 1. If one of them is degree 0, it is not good factorization for reducibility. Okay. So we are taking such a factorization so that our hypothesis that if FAB of F is reducible makes sense. Now because FAB is an isomorphism we saw here. Okay, so Px is some FAB of some Rx, and Qx is also FAB of some Sx. Okay, so now because of ring property, because FAB is ring homomorphism, FAB can take outside and inside left is Rx into Sx. Now you see here FAB is 1 1. It was an isomorphism, in fact, because FAB is 1 1. It happens that Fx is equal to Rx into Sx. Okay. Now this is contradiction. Why? Because this is also factorizing Fx, and Fx is irreducible. This is none of them in unit. This Rx is not unit. This implies Rx is not unit. Any degree polynomial, any degree bigger than or equal to 1 polynomial, they are not units. What are units of polynomial ring? Not unit. Units of polynomial ring, they are just units of actual ring we have taken first time. Okay, this is also proved in the class. In particular, here in this case, this is 0 because case field. Okay, so we see that FAB of F is irreducible. If you have doubt, you can ask. Okay, or let's see it for a minute. Sir, can you please explain the process of checking reducibility? Okay, for 2-3 degree, I can assure something that they are reducible or irreducible. For higher degrees, I don't know any method how to see if it is reducible or irreducible. We'll come to that in the fourth question, which I'm going to do. Okay, if it is reducible, you will find such Px into Qx so that F can be factored into Fx into Qx, and Fx and Px and Qx both are degree higher than, they are not unit in fact. That's all. They are some irreducible element or something else, but not units. You can factor them into non-units. That's all I can say right now. Okay, let's see the last question where we'll see irreducible criteria or reducibility. Okay, so in the last question, what we have is called P test for irreducibility. So let me write last question. This is 1.4. Let P be prime. I should change the color. Let P be a prime number, and let F is that polynomial a0 a1x plus an x power n in zx with P not dividing an. Further, let F bar be a0 bar plus a1 bar x and so on, an bar x power n belonging to zpx. Zp is the ring integer modulo p. Okay, be polynomial obtained by reducing what p, reducing coefficients what p modulo p, so that if, now here is our question, so that if f bar is irreducible in ZPX, then F is irreducible in F is irreducible in ZX. How to see this? What if F is reducible? We want to show that F is irreducible. We will see if F is reducible, we'll get some contradiction. Then it is proved. If F is reducible, then F can be written as some gx into hx. Okay. Where P does not divide leading coefficients of F, G, H. Why? Because if P does not divide leading coefficient of F, it happens so that uh, leading coefficient of F is equal to leading coefficient of G into leading coefficient of H. Now P does not divide leading coefficient of F implies P does not divide leading coefficient of G and P does not divide leading coefficient of H. Okay. Now reducing mod P, reducing coefficients modulo P, Fx can be written as Gx bar into Hx bar. Okay, you can check it that this factorization also hold in ZPX because initially it was like this. Now it can be written as, because reducing coefficient modulo P is also an homomorphism. It will bring homomorphism in fact. So this is Gx bar into Hx bar. Now now here, what is degree of F bar? This is, you can write it as F bar. Degree of F bar is same as degree of F, right? And which is n. Since leading coefficient is non-zero, P does not divide LCF. And initially it was because F is factorized like this, degree of F is same as degree of G into plus degree of H. Let me add extra pages here. Okay, so because F is equal to G into H in ZX, which is integral domain, degree of F is same as degree of G in plus degree of H. And degree of F is same as degree of F bar. We just saw, because leading coefficient, P does not divide the leading coefficient. Okay. What about degree of G bar and H bar? Degree of G bar, this would be less than or equal to degree of G, right? Because once you reduce the coefficients, either leading coefficient will stay non-zero or it can become zero. But in our case, it is not going to be zero because P does not divide LCF, hence P does not divide leading coefficient of G, and as well as P does not divide leading coefficient of H. So degree of them is strictly they are equal. Okay, degree of H bar is also equal to degree of H. And because initially we have taken G and H degree bigger than or equal to, okay, sorry. There could be some different kind of factorization in ZX. For example, F is 2 into X or 3 into X, whatever. So I'm not sure that their degrees are strictly bigger than or equal to 1. What happens to constants? Wait a minute. There is little bit somewhere mistake. Somewhere in this test we have mistake. If you see, 3 is not unit, neither X is unit. Right? So what about this polynomial? 3 into X, it is reducible. What about fx modulo p? Modulo, let's say 5, it becomes 3x, and 3 is unit there. 3 is unit in Z5, or let me write 3 bar. So this is one, this is irreducible. 3 bar x is irreducible, but not fx. So there is a little bit mistake in this question, I think. So any of you can answer this if you have solution. Do you have any solution in your mind, or I am right? Someone also asked the same question in some math website. I was looking into it. P test for reducibility. Wait a minute. If we have factorization into, I mean, they are not constant, but if we have such a factorization that f is not multiple of integers, I mean, when f is monic polynomial, then this proof works. Is it? It is not given here. It just shown that p does not divide a, and then it works, but it doesn't seem to work, right? Or it should say that for every p, if it is irreducible, how to say this? There is some confusion in the statement of this. For a particular, when f is at least okay, let me say if f is monic, then it works. Or if it is not monic, then we should take for every prime p, not a particular prime. If they are irreducible, then it is irreducible here also. What to do then? Assume that f is monic. In place of p does not divide an, replace it by saying f is monic polynomial. Then polynomial. Then you see if f is reducible, then f can be factorized like this, and here degree of g and degree of h both should be greater than or equal to 1. Okay, because it is monic, not a constant multiple. Something like it is not something like 3 into x. Okay, and this is, let's say, 2 into x. This is 3 into x, not like that. The gx and hx both are monic, and they are degree greater than or equal to 1. Okay, if we replace this by saying that f is monic polynomial, then proof works. Then degree of g bigger than or equal to 1, degree of h bigger than or equal to 1, as well as this is same as degree of h bar. This is same as degree of g bar. Now it shows that f bar is also reducible. And this is contradiction because f bar is, we are taking irreducible, and we are showing f is irreducible. F bar is, we are taking irreducible, and we want to show f is irreducible. So if f is reducible, we see that f bar is also reducible. So we shown by converse method, contrapositive method, sorry, contrapositive. So if f is reducible, f bar is also reducible. That's all. But what I am doing is that I'm taking oh, okay, I'm taking f to be monic polynomial. Okay, for no confusion. This part, let me ask someone, my professor maybe, how to do this, or it is wrong or whatever. If p divides, p not divides n. Okay, is this condition necessary, or if it's monic polynomial is necessary? I'll ask, then come back into the next class, then I will explain it. Okay, so for time being, let's say we have proved this. If f is monic, we have proved this. Okay, let's see if we can apply this explanation into following monic polynomials. So here we have x cube minus x plus 1. Note that this is monic polynomial, so that my proof, which I just did, it works. I'm not sure about non-monic polynomials. Okay, something like 3x. I'm not sure. I'll do this in next video. For here, if f is this monic polynomial, we can check it in some zpx if it is irreducible or not. According to that, it will be clear. Let's see if in Z2x, uh, if it is irreducible or not. Irreducible polynomial or not. So in Z2x, this polynomial is same as x cube plus x plus 1, right? Because -1 and +1 both are same in Z2. Okay, so, oh, it is cubic polynomial. If it has factorization hx into gx and degree of them is positive, so what it could be? Degree of h and degree of g. We want both to be non-unit. So of course not degree 0. So one of them has to be degree 2 and one of them has to be degree 1. Okay. So if it has degree 1 irreducible factor, so that degree 1 irreducible factor should look like x plus lambda, and that quadratic one should look like x square plus some linear polynomial, maybe alpha x plus beta. Okay, where alpha beta can be 0 or 1 inside Z2. So from this linear term, we will get lambda is a root of minus lambda, which is equal to lambda in Z2 is a root of fx. Let me write it fx. So if you have root, then this is reducible. If you don't have root, it is irreducible. So let's check. We have only Z2 has only two elements, 0 bar, 1 bar, right? If you evaluate f of 0 bar, what it comes? 0 bar cube plus 0 bar. Sorry, yeah, plus minus doesn't matter here in Z2, and it is 1 bar. It is just 1 bar. So it is 1. This is not 0. F of 1 bar, what it is? 1 bar cube plus 1 bar plus 1 bar. This is 3 mod 2. This is just 1 bar. This is also not 0 again. So what we get is x cube minus x plus 1 is irreducible in ZX. Okay, because it was monic, we can apply our just proof thing. Okay, just proof. What about next polynomial, which is let's say b x cube plus 2x plus 1. If you check into J2, it has 0 or not. At 0, you are getting 1 bar, right? At 1 bar, you are getting 1 plus 2 is anyway 0, so it doesn't matter. 1 bar, 1 bar. So it's the 0 bar. So it has a root. We should take some other place. X cube plus 2x plus 1 inside Z2x. Sorry, Z3x. This time I'm taking Z3x. So what about this? F of 0 is just 1 bar. F of 1 bar is just 1 bar cube plus 2 bar into 1 bar plus 1 bar. This is nothing but 4 bar, which is equal to 1 bar in Z3. So it is again non-zero. What about F at 2 bar? Because Z3 has only 3 elements, we can check 0, 1, 2. At 2, it is 2 cube plus 2 into 2 plus 1 modulo 3. It is 8 plus 4 plus 1 mod 3. When I'm writing mod 3, I'm not writing bar. You see in the notation. So now I'm writing bar. 8 4 bar. This is 13 bar, and this is nothing but 1 bar or 1 mod 3. This is again non-zero. In all case, it is non-zero, right? Z3 has only 3 elements: 0 bar, 1 bar, 2 bar. We checked all things. So this implies that x cube plus 2x plus 1 is irreducible in ZX. Okay. What about next polynomial? Because no one is asking questions. I'm tired speaking. You should be active so that I also find enjoyment talking to you. Okay, so let's see third one, C part. This is x cube plus x minus 1. We'll check if it is reducible. If once we find it is irreducible, no need to check for other primes. Otherwise, we have to search in continuously if it is irreducible or not. Checking reducible is very difficult. Matlab, yeah, irreducibility criteria we have something like P test just now proved. For here, let's say in Z2, uh, Z2, if we reduce f bar in Z2 bar, it becomes x cube plus x plus 1. Evaluated at 0 bar, this is equal to 0 bar cube plus 0 bar plus 1 bar. This is just 1 bar, which is not equal to 0. F at 1 bar, what we are getting here? 1 bar cube plus 1 bar plus 1 bar is equal to 3 bar is equal to 1 bar, which is not again not 0. This implies x cube plus x minus 1 is irreducible. Okay. What about D, where we have 5-degree polynomial x power 5 plus x plus minus 1. Okay. So you check one by one, 100 times, 1,000 times. You don't find it that it is irreducible. Okay. Why? Because it is reducible in fact. If you check for irreducibility, you will never find a contradiction. Okay. I don't know how to see if it is reducible, but let's see. It can, if what happens in Z5x, for example. Let me calculate a little bit. In Z5, if it is polynomial in Z5x, minus 4 can be replaced by 4. Sorry, minus 1 can be replaced by 4. Okay. So it is same as 8 for 5 plus x plus 4 bar. If you have root, then it is irreducible. It is very much clear. Because if one has a root lambda, f of lambda is equal to 0, then x minus lambda is one factor in fx. So this is reducible. F is reducible. So we can check at least if it has roots in Z5 or not. So f of 0 bar, this is just 4 bar, which is not 0. F of 1 bar, this is coming out 4, 1, 1. This is 6 bar, which is just 1 bar. It is not 0. F of 2 bar, 2, 2 power 5 plus 2 plus 4 mod 5. This is nothing but 32, 34, 38. 38 mod 5, which is nothing but 3 bar and which is not 0. F of 3 bar, you can check it similarly. It is what it is. It's 3 into 3, 9, 9, 9, 81, 243. 243 plus 3 plus 4 modulo 5, sorry. It is 7, 3, 0, 5, 0. Oh, is it a root? Sorry, this is 250 or 260. 3, 4, 7, 250. Modulo 5, and this is 0. Is it a root of f? Sorry. Okay, so from it here it is clear. Okay, f is reducible in z 5 x, but we are still not sure that f irreducible in zpx implies that f irreducible in z, but we are not sure f reducible in zpx, f irreducible or f reducible in z. We are not sure about this. Okay, so this conclusion is still, we only have this much. If f is irreducible, we are sure that f is irreducible in zx. If f is irreducible in z5x, we are sure that f is irreducible in zx. But if it's reducible in zpx, we are not sure that f is reducible in zx. Okay, it can be reducible. For example, you take this x cube plus 1, for example. In or x square plus 1 in z2 x, it is reducible, right? This is same as x plus 1 whole square. But in z3x, it has no root. 0, 1, 2. Yeah, it is irreducible. This implies that zx, in zx, it is irreducible. Okay, so but we just proved that f is reducible in z5x. So for proving that f is irreducible, we have to find some p where it is irreducible. Okay, so we are still not sure if it is irreducible or not, but you can check it from somewhere that it can be factored into x power 5 plus x minus 1. This is factored into x power 2 minus x plus 1 into x cube plus x square minus 1. Okay, I don't know how to show this, but this is, so f is reducible in zx. How to show? You check it. If you find this, let me know in the next class. Okay, it is irreducible. Sorry, reducible. What about the last one? E part. It is x power 5 minus x plus 1. If this is your polynomial, take p is equal to 5. Then in z5x, okay, in z5x it has no roots. Check, we can check it. F of 0 z5 is equal to 1 bar only. F of 1 bar is equal to 1 get cancelled and this one remains 1 bar. F of 2 bar is equal to, this is 2 power 5 minus 2 plus 1 mod 5. This is 32 minus 2 plus 1, 31 mod 5. It is just 1 mod 5, means 1 bar. F of 3 bar is equal to 3 power 5 minus 3 plus 1 mod 5. This is nothing but 243 minus 40 plus 1, 241 modulo 5, which is again 1 bar. F of 4 bar, which is last element of Z5, 4 or 5 minus 4 plus 1. This is, if you see, it is nothing but 2 power 10 minus 4 plus 1. 2 power 10, if you remember what it is, I think this is 1024, right? And minus 4 plus 1, mod 5 everywhere. So this is nothing but 1021 mod 5. And this is 1 bar, which is not equal to 0. None of them is root. So this seems to be fx can be factored as gx into hx. The only possibility left is because no linear factor will appear, that g is degree of g is equal to 3, degree of h is equal to 2. Only this kind of factorization can happen. Why? Because if linear factor appears, that will become that will give us a root, and f has no roots in Z5. The only possibility is of this kind of factorization in Z5x. Okay, so if you have this kind of h in factor, so and you have to assume that g bar and h bar irreducible. Further, irreducible. Why? Because if they are reducible, one linear factor will appear in g or h, and that will be the linear factor of f. So it will give a root of f, right? So better g and h should be irreducible. So if you have h degree 2 irreducible in Z5x, so over Z5, if you see Z5x modulo h bar, it is two-dimensional space, right? Over Z5, this is vector space of 2 dimensions over Z5 with basis 1 and x, 1 bar and x. What else you can say? Z5x is integral domain, because Z5 is integral domain. In fact, it is field integral domain. And h bar is irreducible. This implies h bar, ideal generated by h bar, is maximal. Okay, and this implies that 5x modulo h bar, this is a field, is a field. Okay, degree of extension is just this is nothing but field with 25 elements, I power 2 degrees. I hope you understand this terminology. This is just 2. Okay, now here, okay, what we have to show that such h bar will give us a contradiction. Okay, note that x satisfies fx here. This x, okay, in this field, the extended field, f5 square, this can be written as z5 attached with some element omega, which satisfies omega power 5 minus omega plus 1 is equal to 0. This is our given polynomial f. Something which satisfies h, because h of omega is 0 anyway. This will imply f of omega is also 0. That is what is written here. This is nothing but f of omega. Okay. So here Here omega satisfies this condition. Omega H omega is equal to 0. This satisfies, and yes, f of w is 0. Everything is given here. All right. Now from here, if you see, finite fields for finite fields, f upper star, this is cyclic group with dot is cyclic. Okay. In particular, if whatever order is uh, okay. In particular, here it is of order 24. F a star, F25 a star order is 24. So every element, if you power it 24, you will get identity. Okay, 1. So better if you take any element power 25, it will be congruent to the same element modulo 5. Okay, modulo no, sorry, yeah, any element if you power it by 24, sorry, 25, that will be the same element. Okay, I should write like same thing. This theorem, if you remember somewhere, similar thing happens in, I have seen in number theory course. I don't know what its name is. Its name is for any element a power 25 is same as a power 25 can be written as a power 5 power 5. Now a power 5, no, take just that cyclic element, not a random. You take w only, which is generating this bigger field. So omega is same as omega power 25. This omega power 25 can be written as this, and this omega power 25, this from this identity you get omega minus 1 power 5. Now if you expand this, you will get omega power 5 plus 5 into something, you check it. Okay, plus sorry, at the end minus 1 to power 5, and that will be the only one. So this is omega power 5 minus 1. Okay, now write it again, omega power 5, you have here omega minus 1 here. So you are getting omega minus 2 here, and left side is always omega. So this implies minus 2 is equal to 0 in Z5, or this calculation is happening in F25. Sorry, so I should write here F25. So, and this is contradiction. Okay, because minus 2 is not equal to 0. Minus 2 is it can be written as uh, 3 minus 5, and minus 5 is 0 because it is 5 characteristic of this field is 5. So 3 is not equal to 0. That is clear. So minus 2 is equal to 0 is a contradiction. So we got some contradiction at least. So this kind of 2-degree factor cannot appear in F. So what is conclusion here? Conclusion is F has no such H bar of 2-degree in its factorization. So F is irreducible, because only possibility is that either F has linear factor or either has 2-degree factor. So linear factor it does not has. We check element wise, it has no zeros, right?